Good afternoon from Brisbane, ladies and gentlemen. My name is Markus Montigl. I am the president of the IRSE. I also welcome our participants on the live stream, and it's a great feeling to have you all with us here in Brisbane. The title of the paper this afternoon is Human Factors in Cockpits, Lessons Learned in the Light of ATO. And I knew this title already 1.5 years ago, and of course I couldn't know that, which sad actuality this paper would have today in the light of the recent events. However, it is the duty of all engineers, no matter which discipline they work in, to learn also from their mistakes and to do a better job in the future. And so I'm sure we can learn a lot this afternoon from our speaker. Now I have to add that actually I was looking for more than 1 year for a speaker for this paper. It was very hard. There were some candidates, but for one or other reason, none worked out until at the CBTC conference in Toronto, organized also by the IRSE. I met Michael, I had lunch with him, and I immediately knew he would be my man. And once you have heard his biography, you will certainly agree with me. Mr. McNamara started his career in railway signaling, learning signal circuit design in the Signal Design Center of the Penn Central Railroad in Philadelphia in 1973, which later became Conrail. At that time, signal design was performed across 17 states and 2 Canadian provinces for both passenger and freight lines, both electrified and non-electrified. Later, he worked at a series of engineering firms designing signaling and other systems for mostly electrified passenger railways. And in 2003, he joined his current employer, Gannett Fleming, to lead the Gannett Fleming Transit and Rail Systems Division. He has acted as project manager and later as principal oversight on signaling and train control projects across most major passenger railways and in the US and a few in Canada. And now it comes. In aviation, he started flight lessons in 1991 and bought his airplane in 1995, which he still owns. He has traveled in that airplane all across the US, Canada, and even to Mexico. He holds the Airline Transport Pilot Certificate, the highest pilot rating in aviation. He is also a flight instructor. He is a professional engineer in 13 US states plus Ontario, Canada, and since a few weeks he is also a proud fellow of IRSE. Please welcome Mr. Michael McNamara.
Thank you, Marcus. That was very nice introduction. It is interesting to be standing here giving a talk on human factors in aviation in light of recent events with Boeing aircraft, but which I'm following quite closely. To know where we are today, we have to know our history. The railways have been around for a long time, but continuous cab signaling developed in the 1930s in the US is the basis for modern ATO. it became in widespread use across the U.S. In the 1960s. Our 100 hertz carrier systems it was first developed on the major freight railways at the insistence of the U.S. government. Audio frequencies became more popular later on in rail transit passenger systems, metros. Today we have CBTC, and in the U.S. positive train control, which is mandated by U.S. Congress. The systems are more vehicle-centric than wayside. Train position is determined by, in some cases, U.S., or in some cases GPS, but in other places by wheel rotation and transponders. GPS doesn't work in underground stations and systems. For that reason, many of the passenger railways that go underground are using variations of PTC that do not use GPS, whereas the freight railroads that operate across the U.S. are primarily using GPS. Aviation history in parallel. Early autopilots dated back, believe it or not, to 1912, which was only 10 years after aviation started. Advances, like everything, were in aviation were made in World War II. Bill Lear was an early developer both of Learjets and autopilots. Jet airplanes and autopilots are a happy marriage because at the high altitudes that jet airplanes fly at, they are very difficult to hand fly, and I've tried it myself. So autopilots are required to fly at 40,000 feet. Before GPS, which started out, in the 1990s, we had INS, inertial navigation systems, being used for, started out for crossing oceans, and later used across land masses. And of course, space travel to the moon, which was developed in the 1960s, relied on autopilots. Autopilots started out being fairly complicated, as you can see in this picture. That's a typical small airplane autopilot system. Perspective. Railways are a mature technology. 150 years of progress. Aviation was a crazy experiment until about 80 years ago. And it really wasn't reliable transportation until after World War II. Aviation has experienced rapid technological change, where railways, in my opinion, develop change at a more measured pace, although the pace of change in both areas has been increasing rapidly. Again, a little perspective. Aviation, 3 dimensions is inherently more complex. Ask anybody that ever tried to land an airplane and they will understand that. You have to control the airplane both laterally, vertically, and airspeed. But railways have their own hazards. No train can swerve to avoid an accident. We all know as railway signal engineers that trains can't stop in the distance they can see, and that creates inherent risks. Man-machine interface and human factors. The early railway systems used overspeed control while manual driving. The motorman has control and is attentive. Motorman stays proficient. Station stopping adds to his own proficiency. But this creates problems. Modern railway systems use ATO, and the motorman loses proficiency. But headways are more uniform. I'll tell you a little story. There's a passenger railway that I commuted on every day back in the maybe 70s, 80s. It still exists today. It was designed by my company long before I went there. I went in service in 1968. It has ATO in the normal direction only. And they knew that there was a concern about the motorman losing proficiency, so they decided that every day the motorman would make 1 round trip under manual control. So there's a couple issues with this. One is that when he did that every day, he had pretty much full speed commands, and he would slow down at the same places. He slowed down every other day and every other trip. Then, after 25 years, the rail was wearing out, and they had to single track to work on the rail. And there was no ATO in reverse direction. And they had very many close calls because the operators were not very good at operating the trains across the turnouts. They had trouble controlling their speed. Station stopping was always sloppy. And most importantly, they had a few close calls, slowing down for the second turnout to get back onto the normal direction. Because of that, they created a program, which I was project engineer on, to install reverse ATO. It was very expensive and very disruptive to the operation. A simulator to simulate that would have been a better choice. And I'll get into that in a minute. The other man-machine interface issues are that failures are not often well understood by the operators. In railway cab signaling, we've often heard of stories where a train comes to a stop in cab signaling with speed control, and maybe it's because of a broken wire, and then it happens maybe a month later or 6 months later, and the operator takes over manual control, and then one day he comes to a stop again, and he says, "Oh, this happened again," and he bypasses it, and he goes into manual control, and goes around a curve, and there's a train on the tracks. It's because of an incorrect assumption about what's really going on. Aircraft autopilot modes are complicated and confusing for different reasons. I don't know why they're so complicated. Sometimes I think that engineers like to design complicated things, but it gives the accomplished pilot lots of flexibility, but you can't design an airplane for the most accomplished pilot. Less accomplished pilots suffer, and even one pilot that doesn't understand what his airplane is doing can be a very big hazard. In this example, which I was just talking about, where the operator lost proficiency, he was actually unable to control the train when required. Aircraft autopilots can disconnect without pilot awareness, and that's a hazard, especially with two pilots. Each one can think the other one's doing it. Trim, which maybe is something that's not often understood by non-pilots, but maybe you're all reading about it in the New York Times these days, can be an insidious problem in not understanding the aircraft. And many cockpit voice recorders, the last words were, "What is it doing now?" Autopilot thinking in the aviation business has changed. When they first became widespread and they could control all the different modes, the climb, the cruise, the level off at different altitudes. The FAA encouraged pilots to just let George do it. George is the nickname for the autopilot. They figured he's more proficient than the pilot is anyway. He does a better job. He doesn't make mistakes. But what they found out is that when George stopped working, that things didn't go well. Now pilots are encouraged to hand fly part-time. And even in an airline today, most pilots will take off and climb manually till they get to the higher altitudes and then just start pushing buttons. Both aircraft and trains require operators at some time to do some manual operation, and that's important. Lack of proficiency does not have self-awareness. As a flight instructor, I do proficiency checkups on other pilots. And my airplane doesn't even really have a full functioning autopilot because I really don't trust them. But most people that have airplanes like mine and they travel in them, they think autopilot is a mandatory part of their airplane. And but most pilots, if you ask them, well, can you go up and shoot that instrument approach? They, well, of course, I was trained in it. I got certified just 3 years ago. Of course I can still do it. And then they're surprised when they can't, because if you don't do something all the time, you can lose proficiency very quickly. For that reason, the airlines require their pilots to go through proficiency checkups every 6 months, 9 months, 12 months. It depends on how much experience you have. Pilot training is very extensive and lasts many years. It's rigidly regulated and controlled. Applicants can flunk out. They use very sophisticated full motion simulators and very expensive. In this picture here, this is a simulator, and we see two pilots up front. The left seat is the captain, and the right seat is the co-pilot. And they do train as a two-pilot operation, and they switch seats, and then they do the next training session. This guy you see sitting in the back with his computer, he's noticed that he has a computer screen, and he can fail an engine and create different weather scenarios. But notice he has a pen in his hand, and he's marking on a sheet, because he's grading these pilots, and the grades are permanent records. And if those pilots don't pass the grade, they're going to flunk out, and they're going to lose their livelihood. So a lot of attention is applied to this. Pilot training centers on things that rarely happen. When you get into a simulator, or even when you get into a small airplane, which is actually cheaper to run than a simulator, you don't say, well, let's see if you can take off. If somebody's flying the line in an airline, you're not going to say, well, I wonder if you can land the airplane. Well, he's been landing it every day. But what they're going to do, they're going to fail an engine. A pilot in an airliner might go his whole life without ever having an engine fail, but at every simulator session he ever was at, an engine failed. And that's why we use simulators. In other words, the important thing is that we are simulating things that rarely happen. Railway operator training is not so good. It's not often regulated. It's more casual. It's not standardized. The training extent varies. And the railway simulators that I've seen are not impressive. Instead of having that guy say, run this train manually once a day, it would be better to put him in a simulator and say, there's a train stuck on the track. You're going to go over the switch reverse, and then you have to operate on the other track manually, slowing down for curves manually. And when you get to the other turnout, the other interlocking to go back, you have to make sure that you slow down for that to go back. It would be much better to put that into a simulator. And when he's on the line driving the train every day, he can leave it in ATO, which is a better, smoother operation anyway. That's a lesson that we could learn in railways from aviation. Railways could use this training, and should use this training, in my opinion, on a regular basis. Every 6 months, these guys should go through the training, especially if there are scenarios that they're not familiar with. It is legal on most, an accepted practice on most railways to disconnect part of the brakes on the train, typically by truck, which is one half the brakes of a car, and still dispatch the train if there's a problem with the brakes. And we take that into account when we design at our 30% safety factor to our safe braking distances. But we never train our operators on what it's going to be like to drive that train manually with part of the brakes cut out. And these types of scenarios could and should be developed and installed in simulators. Hazards and failure modes, a comparison. Railway signaling fails, it stops the train. Aircraft autopilots fail. They turn it off, but let the aircraft keep going. In some cases, the pilot might not even know it clicked off. In fact, most autopilots, if turbulence gets too bad, for example, it'll click off. It says, I don't know what to do. Click. And warning buzzer and maybe a light. Autopilot's off. And the loud buzzer is to wake the pilot up because he could be half asleep. Hazards and failure modes, pre-departure testing. The similarities are actually very interesting. Both have pre-departure tests, pre-takeoff checklists. They both do the same thing. I've been on many flights when they said, we're canceling the flight. They say you're stuck until they figure out where to get another airplane. I've ridden lots of trains. I've never been on a train that was canceled due to a pre-departure testing. I was on the Long Island Railroad one time, and I was talking to them about cab signaling speed control system, and they had somebody from Signal, now in Saldo, there that was helping to oversee their operation, and they told me that on the certain items the railways, but I suspect not. Certainly, it's not required by law the way it is in aircraft. Large aircraft have a little different because they're complicated. They have a progressive maintenance program. A checks, B checks, C checks. Every 3 months you got to do this. Every 1,000 hours you got to do that. And on those systems, major components are replaced by hours, cycles, and years. We don't see that so much in aviation or in railways. But in aviation, the avionics maybe is automatically replaced every 20 years. Maybe the control head for the navigation system, or maybe some sensors, maybe every 1 year or 5 years. We don't see the requirements for that so structured in railways. I think we could learn from it. In maintenance, railways are different from airlines, but yet increasingly they use some of the same systems and processes. U.S. differs from Europe. U.S. Federal Railway Administration regulates some railways, mostly the freight and intercity passenger railways, but not most public transit, not any of the metro or light rail systems. IREMA, it's an American system that has standards. There's still a culture in the U.S. that railway signal systems want to last forever, and everybody is complaining about the fact that, geez, this electronic thing only lasts 20 years. But aviation has learned long ago that you have to have. Aviation developed after World War II, that's a long time ago, they developed standards called form, fit, function, that all of the boxes that go into an aircraft panel have to have a certain specification for its size and its fit and how it interfaces, so that you can pull it out and put it in a new technology. Railways, not so much. ATO operates 20 hours a day, left out in the weather, and it's typically maintained as part of an overall vehicle maintenance program. The train control engineers don't even have a say, because oftentimes that's like, well, that's the vehicle guys. We don't talk to them. And that stuff can't last forever. There should be a mandated structured maintenance program. Aircraft parts are required to have PMA, Parts Manufacturing Authority. If I want to buy a part for my airplane, of course, you go to the manufacturer first, but manufacturer's going to say, well, we built your airplane in 1965. We don't sell those parts, But there's a lot of airplanes that are very similar to mine. The manufacturer has turned out 50,000 airplanes like mine. Most of them are still in service. So there are follow-on companies that say, yeah, Beechcraft, sure, they'll sell you a part, but they'll charge you a fortune, but we can sell you that part. And, but the FAA requires that company that makes that part to have parts manufacturing authority. It requires quality control, and they'll come and look at your capabilities and your manufacturing site. Whereas in railways, anybody can make parts. BART in San Francisco, it's a ATO system. And it's been in service since the 1960s, and I was out there recently, and the company, which I won't mention, that made the original train control system was bought and acquired, and things changed. They no longer support it. And they were contracting with some little local company to make circuit boards to put in their train control system. And what the safety certification is for that is, well, there is none. So there really should be a better attention to, well, who gave that company the authority to sell those safety critical parts? That really should be addressed. That is addressed in aviation. It's not railway parts. It seems like anybody can make anything. And I've talked to many of these railways, and their answer is, well, we'll just buy a new CBTC system for $200 million. And that really shouldn't be the only answer. So I'll only put these few words here to tell you a little story. So there's a light rail grade separated passenger railway system that I'm familiar with. Our company designed the railway signal system in the 90s before I was there, but I was always been very familiar with the system. It's a cab signal speed control system that's with manual driving. So when the train is over speed, as would happen when you're going at top speed and then there's a step down in the speed commands, so you're immediately over speed, after 6 seconds it goes into a penalty brake to a full stop, unless the operator puts the brakes on. And we call that suppression, because the operator suppresses the imposition of the penalty brake application. The amount of braking is measured by a transducer in a brake valve. Alcohol and drugs are forbidden in both industries. But the area that railways could improve is with medical checkups of their operators. We don't know how many of them, but there has been some accidents. I know of a couple of them recently where a train operator had sleep apnea problems and caused an accident. It actually does happen. Safety certification is very interesting. Early railway signaling, including when I started this industry, had no such thing. In the US, formal aviation safety certification started really with the space program in the 1960s. Today, it's highly regulated and complex. Safety certification in railways, by comparison, in the US is in its infancy, although Europe is much far advanced at this than the US. Railways could learn from aviation. Summary. Initial training, new ATO system or a new line should be sophisticated simulators. And on ATO systems, recurrent training on manual scenarios really is required and has to happen. Maintenance standards in railways, I think, are quite sloppy compared to aviation. The standards should be established by the manufacturer. And in aviation, for build an airplane, they might say, well, you got to replace that engine every 5,000 hours. And the airline or so could say a year or 5 years.
And so I flew from Stuttgart to Vienna, and I asked whether I could have a quick look to the cockpit. And I said to the pilot, I'm from the competition, I'm from railway. And then he said, oh, I never use railways, I don't trust the safety of them. And so he invited me to have the third seat, that cockpit, to actually experience the approach and the landing. And then at some point when we were approaching the airport of Vienna, he started to correct that, not by 10 meters or so, but very generously by hundreds of feet. And I was thinking, hey man, he even doesn't know at which altitude he's flying, so that was a bit a shock. And another quick remark regarding what you said about safety approvals. I can support this because I have been to a maker of airplanes in Switzerland. We don't make cars, but aircrafts. Pilatus aircraft is sold all over the world. And my son is interested in an apprenticeship with them, so we talked to the guy there about replacing aluminium parts by carbon fiber parts in the future. And the story he told me about getting an approval for a new part of the aircraft sounded very familiar with getting a safety approval for a signaling system. And so let's start the questions. We will take questions alternatively from the audience here and from the live stream. And I would like to remind the participants to the live stream that we are not taking any anonymous questions, but please state your name and affiliation in your question. So we start with the audience here. First question, please.
I'm Somnath Banerjee of Ansalves. Hello. Hi. I'm Somnath Banerjee of Ansalves. My question is in relation to the mix of automatic operations and the manual operations.
Yes?
See, unless you may have studied, the overall safety of such a operation is based on the safety level when you have the automatic operations plus the manual operation. Now, to improve the proficiency, you will have or you need enough manual operating times. Now, when you add the two safety levels, will it give an overall higher safety figure which we need to check? Maybe in aviation it will be different from what it is in the railways. My hunch feeling is in railways probably almost no manual working is the highest safety level. Whatever hours you give to manual operation may not effectively increase the safety, but do we have any studies or figures which support the number of manual hours we should provide to improve the overall safety?
I don't know of any studies, but my experience is that in railways there have been accidents occurred when they go to manual operation, and then some things happen which the driver didn't expect. I don't think that the answer is to tell railway operators to drive the trains manually every day. I think the answer is to tell them to leave it on ATO all the time and get their manual experience in a simulator. And in a simulator, we can do things that we can't do in the real world. In an aircraft simulator, which I've been in, we have the aircraft starting on fire, or an engine quits every 3 minutes, or all this kind of stuff. In railways, we should have scenarios where it fails, and you have to take over manual control, and then you have to navigate some complex interlock and things that you wouldn't put the passengers at risk to try and do this. But in a simulator, you can do all kinds of things. And so I think that better simulators is an important part of improving safety.
Do we have a question from the net?
So far, no questions from
Okay.
online. There are 7 people live watching and 25 at some point of time. So you could remind them to come up with questions.
Okay. So all the participants on the live stream are very welcome to ask questions. But we are now taking the next question from the room.
Charles Page from Siemens. A fundamental difference between rail and aviation seems to be that the whole concept of fail-safe in railways. You don't have that luxury in an aircraft. You can't just sort of abandon responsibility and leave the aircraft to its own devices. How do you feel about that concept of fail-safe in railways, how it's changed the design of systems in aviation versus railways? And is it a concept that's probably now a bit naive, that we have to move on from that and take more responsibility more of the time, even when we have failures?
Michael, there's a request from the website. They're asking whether you could repeat the question before answering. It seems
sure.
you're not getting clear from the other microphone.
Okay. The question was, I'll paraphrase it. In railways, we have what we call fail-safe, and in aviation, we don't have the luxury of fail-safe. And I believe the question was, maybe we should get away from the concept of fail-safe. Let me start out by saying that the words fail-safe mean different things to different people. I was talking to somebody once in the hospital business, and he said that their systems were fail-safe, and I'm like, well, what's that mean? And their idea of fail-safe is that the batteries keep everything running until the generator comes on and there's enough fuel in the generator to run it for the next 3 days. So fail-safe is not something that's used in the aviation business, but really in aviation we fail operational. If you look at the instrument panel of a modern aircraft, or even my aircraft, you think, geez, all these different instruments, you need all that to fly the airplane. And the answer is no, you don't. Most of them are just there for redundancy. You could take away 90% of them and you could fly the airplane. And so we have a lot of, in aviation we have redundancy. And we have different ways of navigating, different ways of lowering the landing gear, different ways of doing everything, so that we always, even though I have a single-engine airplane, it's got 2 ignition systems, it's got 2 fuel pumps, one's manual, one's electric, it's got, everything is redundant. And so the words fail-safe are not even used. I think that we should get away from the concept of fail-safe in railways, because there's no such thing as fail-safe. I like to think about a highway grade crossing, and we drop the gates and the flashes are flashing, and we say, well, it failed safe. But if the gates are down, eventually somebody's going to push them up and tie them with a rope and drive across the tracks, because you can't stop the rest of the world. If a train in ATO, if something goes wrong and you say, well, it's fail-safe, it's stopped on the tracks. But those people are not going to sit on that train until their hair grows gray. The train is going to move, and that movement is part of the overall safety situation. So one way of saying this is there's no such thing as an unreliable safe system, and the safety analysis of a railway has to consider what happens when the so-called fail-safe event occurs. There really is no fail-safe. The train has to get to where it's going.
Still no more questions.
I think this is very much in line what I have said this morning. Thank you for that. One more question from the room. I think there is one question over there.
Yeah, my name is David Peel from New South Wales. It's a question relevant to both industries, really, and it's regarding the balance between self-certification and safety authorization from an independent perspective.
So the question was the balance between safety certification and an operation?
Independent safety certification compared to self-certification by the manufacturer or supplier.
Yeah, ISA, independent safety certification, is compared to self-certification by the supplier. In aviation, that's a very good question, by the way. In aviation, the Federal Aviation Administration, the U.S., and probably agencies around the world, would not trust the manufacturer to be the sole determinant of the safety of the aircraft. For one thing, an independent analysis is always called for. Interestingly, in aviation, they don't have this concept of a third-party independent safety thing. It's not done that way for some reason, but that we have in railways. But it actually is something that in aviation is talked about a lot. As airplanes become more complicated, it's more difficult for the FAA to hire some people and say, you go look at Boeing and tell me if it's safe, because, well, it's a complicated story. What, are you going to read the software code? They're not. How are they going to do that? So increasingly, as a complexity is requiring more of the safety certification to fall on the manufacturers, and there are people in the aviation business that are unhappy with that, and there is discussion currently about what to do about that, and I think in light of the recent accidents, there's going to be more thinking about that, because in perspective, somebody could have looked at this and said, you're going to do what? You're going to have an autopilot that works when the autopilot's turned off, and it just doesn't make sense, maybe. And so it's a good question, and there's a lot of discussion about that. Railways don't really have that much complexity, so, but I think that an independent safety certification is important, and I don't think we should rely on the supplier who has a financial incentive to simplify the certification process.
A very interesting answer. This may be appearing impolite, but I also have a question which I have to ask. It is also related what was said in the previous talk, and this is about the degree of automation which we should achieve. I think there is a lot of controversy going on about this. Some people say everything should be fully automated, from cars to trains to planes, so no human ever touches any button and whatnot anymore. And others say this is not possible, and so we should deal with this very carefully. You hinted at it when saying what your opinion on your own autopilot was. Can you, very brief, otherwise Sundar will kill me. Just 2 minutes.
And they got that question, right? It's an interesting question. The from my own perspective, everybody that's reading about this Boeing 737 now knows that, boy, this elevator trim is a really dangerous thing. I've always known, most pilots have always known, that elevator trim is a very dangerous thing. Most airplanes, all the big airplanes, but most airplanes, even like mine, have electric elevator trim. Mine doesn't. And it's that way on purpose. I have to manually move a wheel. So, and a big advantage is that I always know what it's doing because I did it. But there is a lot of talk about humans. In railways, there is a lot of talk about driverless trains, and I've actually worked on a system in Los Angeles that was proposed to be driverless, and they never really got there. And in the end, they said, well, we're going to have somebody on the train anyway, because, you know, what if somebody picks a fight with somebody else, or somebody tries to pry open the doors, or something stupid happens. And so we got to have a person on the train. And if we're going to have a person on the train, well, we might as well have him sitting up front. And if he's sitting up front, why don't we just have him sit there and push buttons? So you say, well, why would you want to have a driverless train if you got to have a person on there anyway? And maybe he just looks at tickets. But so I personally don't believe that we should go to zero human involvement in these complex systems. I don't believe that we should go to airlines with only one pilot, even though a lot of small airplane airlines operate with one pilot, and I think that's okay. But if you have 300 people sitting in the back, I don't know why you'd want to go to one pilot or no pilots. I think that's ridiculous. There's a lot of interest these days in pilotless quadricopters that are going to carry people into downtown city centers. I'm not getting in one of those. And I don't know why you would want to not have somebody that understands the machinery and the system and the environment with some training to have some advice.
Thank you very much for this clear statement, and please join me in
It's just in time. There's one question coming,
Okay.
but it is very close
It's
to
your
what-
responsibility.
Yep.
Can
It
you
is-
read it out
Yeah.
here?
It is very close to what Michael was talking about now, but still I'll read it if he wants to add on. Railway signaling engineers have attempted to remove the human element through initially interlocking and now ATP systems. It seems many aircraft accidents are caused by human error. Is the industry trying to eliminate this?
Well, it's very, very interesting to say that aviation accidents are caused by human error. In light of what's going on today in aviation, I like to say that the accidents are not caused by human error as much as they are caused by misunderstanding of the man-machine interface, which is really what this whole talk is about. But it's how humans and machines interact. And with these recent couple of accidents with the 737, you're going to find out that the problems did not occur in the air. You're going to find, everybody talks about, well, the angle of attack sensor failed. Well, I can tell you that an angle of attack sensor on a Boeing airplane doesn't just fail when it's 2 years old, so that didn't happen. Somebody on the ground damaged it. Well, how did they damage it? Well, we don't know, but I'm sure you're going to see, as part of the airworthiness directive that's going to come out, there's going to be big signs on the side of the airplane saying, when the airplane's parked at the gate, stay away from this thing. You're also going to find that there's, in my airplane world, where I have my own airplane, I take it to a mechanic to have him work on it. He doesn't have any supervision. Most of them operate as sole proprietorship. And we always talk about